My name is Lisa Stewart. Welcome. I am the Chief Administrative Officer here at the Kavli Institute for Theoretical Physics in Santa Barbara, California. Welcome to the talk that you're about to hear by Caprice Phillips, who will be presenting the 10th in this National Society of Black Physicists talk series called Innovate Seminar Series. The prior talks in this series are posted both on NSBP's website as well as KITP's, in case you have missed any of them or want to watch them again. Today's talk will be approximately 30 minutes and it will be presented in webinar format. We're going to hold the questions until the end, so as they arise for you throughout the talk, please go ahead and enter them real time into the Q&A. And then following the talk, our speaker will address the questions. Before I pass over the baton to Farah Simpson to tell us more about the NSBP series, I want to just briefly mention a couple of programs that we have here at KITP, the Kavli Institute for Theoretical Physics, that may be of interest. One is our existing Graduate Fellows program, and that is intended for graduate students, and in partnership with their advisors, they can be supported to come here for 6-month stays, and it's an opportunity to be exposed to all sorts of science from different faculty from around the world who come here on a regular basis for various programs. The other is a really exciting new development, and with great gratitude to Stefan and the National Society of Black Physicists in helping us to co-create this idea. It's called the KITP Fellows program, and that is focused for faculty members at minority serving institutions that are primarily teaching universities. And it's a 6 to 8 week stay for the faculty member to come here and participate in the science that's happening here. I'm really excited about this particular program. So I'm going to pass it off to Farah here to tell you more about the Innovate Seminar Series, but I'm also going to drop these links in the chat for you, so hopefully you'll have a chance to take a peek. Thank you, and it's your turn, Farah. Thanks.
Hi, everyone. Welcome back to our NSBP Innovate Seminar Series. This seminar series was created by the NSBP Student Council as a way to give a platform to our members to share their research, but also for NSBP members to be able to talk about their research and also hear about other members' research and just display their research ideas and projects in a non-specialist way. So we're super excited to have Caprice today, another student member. We're always excited to have student members share this platform and share their research with us. I hope that everyone enjoys it, and please continue to attend our seminars, which we have every single month at the end of the month. And I'll pass it over to the president of NSBP, Dr. Stefan Alexander.
Thank you, Farah. Thank you, Lisa. Thank you, NSBP Student Council, for hosting this wonderful seminar series that really provides a great platform for students and faculty, researchers, and NSBP land to share their research. I especially want to thank Nico Cooper and Farah for getting all these great speakers, and very excited to hear this exciting research program of Caprice Phillips, who is a PhD student at the University of Ohio State University, which used to play Penn State, very let's say a competitor of Penn State in various sports, as Caprice very well knows, where I was as a junior faculty. And Caprice is from Little Rock, Arkansas, where she did an undergraduate in physics and a minor in mathematics. And then she went on to do a master's at the University of Texas, Austin. And then she went on from there. Now she's at Ohio State. And we're very excited and proud. And also a recent NSBP member just graduated, Jamal Givens from Ohio State, does PhD, and now he's a postdoc at Princeton along with Delilah Gates. So things are starting to really happen. And so anyway, on that note, oh, there's one more thing. Caprice, her hobbies are cooking, botany, or plants, I guess you said the plants. And what else? Theater, or i.e. Netflix, and coloring. So the title of your talk is Detecting Biosignatures in the Atmospheres of Gas Dwarf Planets with JWST. Okay, it's all yours, Caprice. Thanks.
Okay, thank you. Thank you for the introduction. Let me share my screen. Stefan for the introduction. And so, like Stefan said, like my name is Caprice Phillips, and my pronouns are she, her, and hers. I'm a third-year PhD student at the Ohio State University here in Columbus, Ohio, and I work with Dr. G. Wang on detecting potential biosignatures in the atmospheres of gas dwarfs with JWST, and that's what I'm going to be talking about with you guys today. So before I get started, first we move the Zoom thing. So before I get started, I wanted to introduce again my advisor and our collaborators. So we have my advisor Ji Wang here, and Sarah Kenju, who works at the Space Telescope Science Institute, Tom Green, who works at NASA Ames, Renyu Hu, who works at JPL, Joe Schultz, and Dr. Winnie Pinero here at OSU in the Earth Science Department, and Jeff Valenti, who works at the Space Telescope Science Institute. And so like we have a really great team. We have like folks who are experts with like different instruments aboard JWST, like MIRI and NIRSpec, and we also have Renyu Hu, who does a lot of photochemical modeling. And Joe and Wendy have been really great as far as like the earth science, geology part, and interiors for this project. And Jeff Valenti is also an expert with the NIRSpec instrument. So I just wanted to give them a shout out and like thank them for their assistance with the work and the paper that just came out. So before we get started, I wanted to start with an overview. So basically what I'm gonna start with an introduction. We're gonna talk about gas dwarf planets, what exactly are those things, and talk about atmospheric biosignatures, and then go into ammonia as a potential biosignature. And then I'm gonna talk about detecting ammonia in the atmospheres of gas dwarfs and some of the simulations that I've been doing, along with some next steps, and then go on into some conclusions and summary. So in astronomy, and specifically in exoplanet science, there are a lot of open questions, and they include like, do we want to know, do other Earths exist? Like basically, is Earth unique? Are they common? Do they have signs of life? And what will those signs of life look like? Those were some of the main drivers in exoplanet science and just astronomy in general. And so if you're not in astronomy or exoplanet sciences, we have this mandatory plot that we have to show everybody. So basically it's this cumulative, on the y-axis is total number of detections versus year. And so this is kind of showing the total number of exoplanets that we have confirmed, and seeing as it increases in years. And so I wanted to point out that, like, you know, the Kepler spacecraft launched in about 2010, and we started seeing a bump and the number of exoplanets detected, especially with these different methods called transits. And so these colorful ones over here are just the different detection methods. And the one I wanted to point out is green. So like thanks to Kepler and TESS, we've discovered like thousands and thousands of exoplanets, like shown in the green through the transit method of detection. And we have over 4,000 total confirmed exoplanets to date that we've been looking at. And so, all right, so getting into, so what are gas dwarfs? And in case you're like not that familiar with like astronomy or exoplanets in general, like an exoplanet is really just a planet that orbits a star other than our sun. It's outside of the solar system. And so gas dwarfs, we found, are some of the most abundant type of planet found through the transit method of detection. And so an astronomer in 2014, Butchave, came up with, he classified exoplanets based on the metallicity, or how many metals were in like the host star. And so we kind of broke the exoplanets down into like three main regimes. Like below 1.7 Earth radii, he said that those were likely to be rocky planets, and above like 3.9 Earth radii, he said those were likely to be gas giants. And so between that regime, between 1.7 and about 3.9 Earth radii, they dubbed these planets gas dwarfs, which are planets with rocky cores with hydrogen and helium envelopes. And those include something called super Earths and mini Neptunes. And so basically, so what we're seeing here on this plot here is, again, like the number of planets broken down into like the planet type. Is what I wanted to highlight is that super Earth size and sub-Neptune size are some of the most commonly typed planets found through the transit method of detection. So they're of great interest. And so what's interesting about gas dwarfs is that they're not found in the solar system. So we're a very, very structured kind of solar system. You know, we have the inner rocky planets, Mercury, Venus, Earth, and Mars. And then we have the gas giants, Jupiter and Saturn, and then followed by the ice giants like Uranus and Neptune. So Earth is the most massive terrestrial type planet. And so we don't have something like super Earths and many Neptunes here. And so it begs the question, are they scaled up versions of the inner rocky planets, or are they scaled down versions of like the gas giants, and like what stopped them from becoming gas giants? A lot of questions about how did they form, what do their atmospheric compositions look like, interiors, kind of a lot of open questions kind of come into play with these type of objects. And so they're more massive and larger and more common than Earth type planets. So they're really unique exoplanets that's characterized and search for biosignatures. And so because they can have different atmospheric compositions, we're interested in what kind of biosignatures may be on these type of planets. And so that's one of the ones we're going to talk about is ammonia. And again, we're going to be looking to see if JWST can be able to detect this biosignature. So I wanted to switch gears a little bit and kind of like take a step back and exactly like, what is a biosignature? You may be wondering that. So like basically an atmospheric biosignature is a gas whose presence in the atmosphere indicates that the planet likely harbors life. And so their Meadows and Seeger, two astronomers and astrobiologists, kind of came up with three main criteria for what a biosignature could be. You know, we want it to be generated by life. It has to build up in the atmosphere to actually detectable levels, and we want it to be present, active in the wavelength range being observed. And so, you know, once you have a biosignature, you know, we want it to be something that's ideal, for example. And so they kind of came up with like these 5 criteria. Again, like, does it exist? We don't want it to exist naturally in the atmosphere at kind of ambient temperatures and pressures. We don't want it to be created by geophysical processes like volcanic activity, for example. Not produced by photochemistry, also not easily destroyed by photochemistry, and have strong spectral features. So like, for example, if we were to take like nitrogen, which is about like 78% of the Earth's atmosphere, it makes up a lot of the Earth's atmosphere, and also can have like biological like processes that produce it, but there's no rotational vibrational modes like for this in the visible and infrared. So like we can't detect it, doesn't have a strong spectral feature. So like N2, like nitrogen, doesn't make a good biosignature, for example. And so kind of moving on to what I've been promising you, ammonia as a potential biosignature. So in 2013, astronomer astrobiologist Dr. Sarah Seeger was first proposed ammonia as a potential biosignature in the atmosphere of these cold Haber planets. And so this was kind of named after the Haber process here on Earth, which is the main industrial process for producing ammonia. So basically what you need like nitrogen from the air and like hydrogen and an iron catalyst to make and uses this to make ammonia. And so you need really high like pressures and temperatures to make this happen. And so Sarah Seeger is like, okay, like this could be a potential biosignature in hydrogen and nitrogen dominated atmospheres. And the idea is that like microbial life can break apart the bonds in hydrogen and nitrogen to produce ammonia, and it would build up and accumulate into the atmosphere, hopefully to detectable levels. And like this makes like a strong biosignature, is a strong candidate for a biosignature for a number of reasons. The first is that it is easily destroyed by chemistry and like volcanic activity, which means that if you were to see ammonia present in the atmosphere, there could be the idea is there must be something replenishing or making it. So it might be like a life process that's causing that, for example. And also ammonia has like lots of features that you can detect. It has strong spectral features. So there are a lot of like good reasons why like ammonia can be like a ideal biosignature in hydrogen and nitrogen dominated atmospheres. And so basically in a series of papers, so in 2013, she had a series of papers kind of creating like theoretical spectra for what this might look like on a cold kind of habit world. And so what we see here is like basically flux on the y-axis, like energy, and then from the 5 to 30 microns. And then we see here it's like a 25% hydrogen atmosphere with like 75% nitrogen. And so like they created like NH3 ammonia. They had like a smaller amount, 0.4 ppm in the atmosphere, and then they also changed the concentration to be like 4 ppm. So we see like as you add more ammonia, you get like a deeper feature here, just kind of showing how that affects it, and that's where the feature would be in the mid-infrared here around 10 microns, for example. And so she also did the same thing for theoretical transmission spectra for a cold harbor world. So we can see that there's, like I mentioned before, that there are a lot of ammonia features to look at in the near infrared, also in the mid infrared. And so, and this one, it was like 90%, it was more hydrogen in the atmosphere, and they also varied the amount of ammonia present, like it goes from like 0 ppm to like 500 ppm. And so you can see like as it just like 0 ppm going to 5 to 500, like you get an increased signal because there's more of it in the atmosphere. So this is just kind of showing like how the spectra like might look for these theoretical worlds, for example. And this is the base of the foundation for the start of this work. And so, you know, I'd be remiss if I didn't mention that there are there can be like false positives for ammonia. And so the first one is, you know, a rocky world with a hot surface temperature of like 820 Kelvin, which could be produce ammonia by that Haber process if it was like an iron surface. And then there's also naturally occurring ammonia in the atmosphere of gas giants and some many Neptunes. And there's planets that have like outgassed ammonia during evolution. Basically, they've like gotten rid of their like primary atmospheres, and like they like interior like vented out like ammonia from the interior to like produce an atmosphere. So it wouldn't be produced by like life. It's something like within the planet. And then also there could be ammonia ice brought from comets that could be like false positives for ammonia, for example. So there's also something you have to take into account for this research as well. All right, so I don't know how familiar folks are just with astronomy in general, or how exoplanet science work, but I wanted to talk about like transits. And so basically what you have is you'll have a star, and you have a planet that will cross in front of the star, and we can peek into the planetary atmosphere this way, and that's called transmission spectroscopy. But then when the planet, you know, when it goes behind the star, is called like secondary eclipse or thermal emission. If it's like tightly locked, like one face of the planet is like facing you, like the permanent day side, you can get like thermal emission from the planet. You can peek into the atmosphere that way, and you can like utilize different instruments and stuff to do transmission versus like emission spectroscopy. So this is kind of what transits are all about when I talk about whether a planet like transits or not in front of a star. And so this spacecraft like JWST is going to have like unprecedented light collection and wavelength coverage. It's like almost about 3 times the size of the Hubble Space Telescope, and it goes from about 0.6 to 28 microns, which is visible to mid-infrared light, and Hubble goes from 0.1 to 2.5, which is ultraviolet to near infrared. And there's going to be a lot of like various instruments aboard JWST that's going to help us probe planetary atmospheres, like NIRSpec, the near infrared, and MIRI in the mid infrared, for example. So I wanted to test like how well these instruments could be able to detect ammonia should it be present in the atmospheres. And so here is kind of a breakdown of how my research project goes. And so goes or went, the paper's out, I'm not sure which word to use. But so first we choose amount of ammonia in the atmosphere, and we start with 4.0 parts per million kind of base atmosphere based on Sarah Seeger's work. And then step 2 we go over here and we choose an instrument / mode. And so, like, for example, with MIRI LRF, we wanted to test that secondary eclipse or thermal emission to see if we could detect that 10 micron ammonia feature. And so we choose this instrument, and then step 3 is we change the amount of hydrogen present in the atmosphere, like based on what I showed before, like they went between 90% hydrogen versus 25% hydrogen, which corresponds to a low mean molecular weight versus high mean molecular weight atmosphere. And for like the MIRI, for emission spectroscopy, we want to ask is like the flux of the planet over the star, is it greater than the sensitivity for the instrument? Like, does this instrument have the capability to detect this? And so we go back and we do the same thing. We go back to step 2 here with a different instrument with like transmission spectroscopy, for example. We use like NIRSpec or NIRISS, for example, and we vary the amount of hydrogen in the atmosphere, again, with a low mean molecular weight versus high mean molecular weight. And then for low mean molecular weight, we also want to test the effects of these pesky things called clouds in the atmosphere. And so we either account for or not for clouds in the ax, like is statistically significant detection, so like greater than 3 sigma, for example, for this kind of transmission spectroscopy with these different instruments. And so before we can start to, work on this, like we have to actually build the spectra for the planets. Sorry. So we use something called petitRADTRANS, which is basically this code. It's this radiative transfer code that builds spectra. And so what you can do is you can input a bunch of different things about the planet, like you can change the surface gravity, the pressure temperature profile, you can account for clouds, like where they're at in the atmosphere, the abundance of things, like how much ammonia is present, like other different species, for example, and you can set like where your pressure is you're looking at. You can also change the equilibrium temperature, the mean molecular weight, and like the size of the planet, for example, and it will spit out a simulated transmission versus emission spectra. And so, so I forgot to mention Paul Moliere in 2019 developed petitRADTRANS. And so basically here is kind of the same thing, like on the left, those model inputs that I talked about. And then on the right here, we have the model outputs. And so this is just an example of what Petit puts out, excuse me, that I work with. This is transmission spectra, like in the near infrared here. And then on the bottom here is emission spectra in the mid infrared from like 5 to 12 microns, for example. So this is kind of the initial data that I work with when it spits out from Petit. So again, before we can start this project, we have to actually have targets to test it on. So we have to like narrow down targets. Before I mentioned there are like 4,000, like over 4,000 exoplanets, and like, we can't test them all. So we have to select targets. And so we have like 3 main criteria for like how we selected our targets. We first asked like, is the equilibrium temperature like less than 450 Kelvin? Like, is it between a certain size, like 1.7 to 3.4 Earth radii, and is it less than 50 parsecs away? And so this criteria was selected first, like the equilibrium temperature less than 450 Kelvin is where water can exist like in a liquid state at like 10 bar pressure, like for example. And then with a 1.7 to 3.4 Earth radii, the lower cutoff, 1.7, is to make sure that it has a gaseous envelope, and 3.4 is to make sure that the pressure isn't too high that it could produce ammonia abiotically, for example. And less than 50 parsecs away, like we want it to be like to have adequate flux, be able to see it like from the host star and the planet. We don't want it to be too far away, basically. And so based on this, we got out about 7 targets that met the criteria. And so this is a plot showing here of the planet radius versus equilibrium temperature. And so our targets that we selected are in color here, and then the ones like in the gray dots are the ones that met the first 2 criteria with the equilibrium temperature and the size, but were more than 50 parsecs away. And so some of the ones of interest are like K218b that you might have seen like in the news, had like water vapor detected in its atmosphere. It's in the habitable zone of its stars. So that was one really famous one, for example, that a lot of exoplanet people are really excited about. And so low planetary flux makes atmospheric characterization challenging. So basically what I have here is a plot of the planet flux, like energy coming from the planet versus wavelength in the mid-infrared 5 to 11 microns. So this planetary flux is like very low, and so it's higher with a high equilibrium temperature and like it's lower as you go down to a lower temperature of the planet. So it's like really hard to detect things because they're so faint, and these features over here is what we would be looking for, and this is like a very faint flux for the planets, which makes it like very challenging to characterize their atmosphere this way. And so basically, like when you do to see if you can detect ammonia with the flux of the planet over the flux of the star, and so like I said, there's a ammonia feature around 10 microns around here. So I should have put a box here, but it's around 10 microns here. And this little dashed line here is the noise floor for the MIRI instrument for like 10 transits. So basically like the signal, the flux contrast from the planet and the star needs to be like above this dashed line here to be able to be detectable. So already we see like there's like at least 3 that are kind of ruled out here, and there are a few above here, but it's kind of like they're basically, even though they're above this like systemic noise floor limit, they're too faint to be like detected. They're limited by like this thing called photon noise. And so even though they're above like the systemic noise instrument, they're still too faint to be like detected. So we kind of like ruled out targets and this specific instrument mode for these things to be able to detect it, for example, which is just as important as kind of ruling in targets versus like ruling out targets, for example. So, but there's no need to panic because ammonia has many features like in the near infrared. So like what we were looking at before was in the mid infrared from 5 to 12 microns. So what we're looking at now is a plot showing ammonia features in the near infrared, and each of these spikes are kind of prominent ammonia features, like around 1.5, 2, 2.3, 3.0 microns, for example. So there's lots of features in the near infrared to see if we can detect them, even though it's hard to see it with emission spectroscopy in the mid-infrared. So basically, what I did is I simulated the spectra for the targets, and I also simulated how the observations would look with this tool called PandExo that Natasha Batala developed. And so basically what we have here is the transmission spectra for an example target. And so the orange is a theoretical spectra that I built using petitRADTRANS, and the black dots, and then different like colored black dots here are the simulated data points for JWST. And this is just kind of showing where the different instruments cover, for example. And on the bottom is the corresponding signal to noise for the features. And this is a 90% hydrogen atmosphere spectra. And so basically what I did is I looked at each feature, for example, like the 1.5 micron ammonia feature, and we can see here that it has like around 5 signals of noise. And this is good. It's like greater than 3 signals. So we say like, yes, like we would be able to detect this ammonia feature like in this planet, like given its like planetary parameters and how far it is away, like we get a 5 sigma detection for this feature here. And so I did the same thing, but lowering the amount of hydrogen in the atmosphere. This is the same target, the same wavelength coverage. But when we look over here, we see that it's around like a 2 sigma, 2 to 3 sigma, like signal to noise. It's like it decreases like 1 over mean molecular weight, which is the amount of hydrogen in the atmosphere. So we have less hydrogen, we have a less signal to noise correlation, for example. And so another thing that I wanted to test was how changing the amount of ammonia in the atmosphere changes the signal, for example. So Sarah Seeger said that the concentration of ammonia in the atmosphere is proportional to how much biomass or material like microbial life on the surface of the planet. So this plot is the same thing that says transmission spectroscopy, and it's the signal versus like kind of wavelength region here in the near infrared. And so basically, like we look at this 1.5 micron feature again, like if we see that there's like the black is like 0.4 ppm, like the signal is like kind of small. And then, but if we increase it to like 400 ppm, like the signal strength like drastically increases, which will increase the signal to noise, for example. So basically, like a stronger signal, like I said over here on the right, equals like more biomass and surface, more material that's creating this ammonia. And so a weaker signal would indicate that there's less biomass or less like maybe microbial life like on the surface, like creating this signal, for example. And so I mentioned before that in astronomy, we have this pesky little things called clouds that make beautiful sunsets, but they're kind of really pesky in exoplanet science. And so we found that, you know, clouds do hide and weaken ammonia features. So basically, if you have a cloud that's like higher up in the atmosphere, like your spectra kind of appears flat, which makes your signals of noise very weak. Versus if you have a cloud that's like lower in the atmosphere, you're able to see like more of the ammonia features, like in the pink here, and it doesn't make it as flat, and you're able to like get features out, for example. So that's another thing that we wanted to explore, was the effects of clouds on how we can detect ammonia. And so basically this project kind of like the accumulation was this kind of ranked list of targets where we took like different ammonia features, like there's different ones like 1.5 to 2.3, 3 microns, and we found the signal to noise and found like the average for that, and we created a ranked list of targets that would be best suited for observations with JWST and like certain instruments. So we have the example I've been showing is like TOI 270C that's ranked best because it has a high signal to noise. And then like one of the targets, JG 143B, is ranked last because the host star is like super bright and it's saturated, and it's like too much for the detector, and it saturates it, and so it won't be able to be observed with those specific instrument modes that we looked at. And two of the ones that I highlighted here, they're really good targets of interest because they have more constrained like mass and radius, which is like really good for like modeling more like the atmosphere and like interior of the planet. And so they're like really targets of interest in the exoplanet community to follow up on as well. And so basically I wanted to just kind of start putting up my summary conclusions. So like basically like gas dwarfs, you know, they're more massive and common than Earth-like planets and are promising sites to look for signs of life. And, you know, ammonia is a really cool exotic biosignature unique to hydrogen and nitrogen dominating atmospheres of gas dwarfs, which includes super Earths and Neptunes. And we found that the NIRSpec and NIRISS are better instruments than MIRI LRS to detect ammonia. Like they're better for with transmission spectroscopy, the primary transit, than emission spectroscopy with MIRI LRS to detect ammonia features, for example. And we saw that the detectability of ammonia is affected by like how much ammonia is in the atmosphere, the concentration, the mean molecular weight, basically how much hydrogen is present in the atmosphere, and the presence of clouds, for example. And so kind of what are next steps for me? So OSU is a founding member of the Twinkle mission. So, you know, there's going to be a lot of like competitive time for JWST, and like this Twinkle mission is like focused on like exoplanet science. So I'm like working with the Twinkle mission as well to like help select best targets for observation, and also to see if like this Twinkle satellite and will be able to detect ammonia as well. So that's kind of what the next step. Oh, sorry, I forgot to turn off my sounds. The next step for me is kind of like trying to take this study and applying it to Twinkle as well. And so, yeah, I just wanted to say thank you, like give a plug for my website and like my contact information, and to, you know, check out stuff for Black and Astro. We have a travel scholarship out for AAS. And I just wanted to say also, and to take any questions in that, like my paper is up on the archive now. If you have your phones, you can scan the QR code, it'll take you to the paper, and here's just a screenshot of it. And with that, I'll take any questions. Sorry if I talk really fast, but I got excited. So, but thank you.
Thanks so much, Caprice. I'm really happy with that we got this organized and were able to find someone doing things in exoplanet science, which is essentially like a very large field, but not something that we've really focused on in the past for Innovate yet.
Yeah.
So I guess I will wait a little bit for people to think of some questions to ask and post them in the chat. But in the meantime, I do have one question for you. And I'll admit I'm a theorist, so I don't have any, particularly technical question for you about your particular field.
That's okay.
But I guess I'm thinking James Webb hasn't been sent up yet. But I guess once it's in orbit and taking data, what would be your dream about the data that it would collect, and what would be your absolute nightmare?
So I think I'll start with the more optimistic one. So my dream would be that I think it'd be really cool if we were able to detect ammonia. Like, of course, like detecting ammonia isn't a telltale sign that there's signs of life, but it's somewhere to like start to like rule out like abiotic or like non-life producing like processes to like start that work on that. I think it'd be very interesting because like, I'm kind of new to the astrobiology field, but it's such an interdisciplinary like field, and you need to talk to chemists, biologists, geologists. Like, it's like kind of like a cool collaborative network. So like talking with people, experts like Vicky Meadows and stuff would be like really interesting. Like if we were to detect ammonia, like what do we do after that? So nightmare, I don't know. It doesn't launch. I don't know. You said after it launched though, but it's like a gag in like the astronomy community that's never gonna launch. But I don't know. I guess that would be my nightmare that it didn't launch or something like that. But I don't know. I don't have anything else. Sorry. That was a really cool question.
Yeah. So I guess as long as it does take data, that would still mean that would still mean that there's a job to be done.
Yeah, there's always something to look for. I think there's always cool science to be done.
So if anyone else has any questions, yeah, please feel free to post them in the chat, and we'll be able to answer them here.
Sorry. Yeah, this was like perfect timing for to give this talk, because lately my paper just came out on the archive. I think this Tuesday. I mean, this week feels like it lasted like 10 years, but the paper just came out this Tuesday, so it's like really, really nice.
I've never seen a QR code for plugging your paper, so that's a habit that I'll have to pick up.
Yeah, just scan it and it'll take you right to it.
All right, so we have one question from Professor Chandra Prescott-Weinstein. Can you explain for a particle theorist what the difference is between looking for biosignatures around gas dwarfs and other types of planets? Something I can summarize for other people and sound coherent.
Let me think. So that's a really good question. So I think so. The kind of thing with gas dwarfs is that they have, like, if you compare to like Earth-like planets, for example, like gas dwarfs, they can have hydrogen and nitrogen dominant atmospheres. So ammonia is like a unique biosignature to that type of atmospheres. But if you're looking for other like Earth-like type planets, you might be looking for like O3, or some people may look for like methane because they have different atmospheric chemistry. So you're looking for different types of signs of life or biosignature, because the atmosphere is made up of different like materials and stuff. I hope that answers your question. I hope it sounds coherent. So yeah, basically it's because the atmosphere is made up of different stuff that you're looking for different types of biosignatures.
Thank you so much. So if there are no more questions, at least that people immediately have on mind, I want to thank you again. Thank you so much for for giving your talk and, you know, being incredibly accessible, I think. And I want to thank everyone for coming to be able to engage with some really incredibly interesting science.
Thank you. I had a lot of fun.